What's up, AP Physics Mechanics students? Welcome back to our elegant physics videos. Today's topic 5.4 rotational equilibrium and Newton's first law in rotational form. So let's jump right in. Translational and rotational equation. Consider an extended object of mass m acted on by a set of forces, for example, F1, F2, F3, and F4. Now, in physics, an extended object can respond in two ways. It can translate, meaning move from one place to another, and it can rotate, meaning turn about some axis or pivot. So, to fully analyze the motion of an extended object, we need to check both. Translational equilibrium. The object is said to be in translational equilibrium if the forces are balanced. So, the net force is equal to zero. That means fx, or the summation of fx, equals 0 and the summation of fy equals to 0, which gives the birth of two linear equations. In other words, along the x-axis, forces must cancel out, and along y-axis, or y direction, forces must also cancel out. No net push, no net pull, no linear acceleration, and the object remains at rest or it moves with constant velocity. This is direct consequences of Newton's first law of inertia. So if the forces are balanced, the object will either remain at rest or continue moving with constant velocity. Now let's move to the second layer of the system, the rotational equilibrium. The object is said to be in rotational equilibrium if the net torque of the applied force about certain pivot sum to zero. So tau net is equal to zero. This gives us one rotational condition or give the birth of one linear equation. And here is the key idea. Even if forces are balanced, the object may still rotate if those forces create a non-zero torque, no net torque, no angular acceleration, and the object remains at rest or it rotates with constant angular velocity. So force balance alone is not enough for a fully equilibrium case. For complete equilibrium, we need both conditions together. Translational equilibrium, the sigma fx equals 0 and the sigma fy equals 0, and rotational equilibrium, tau net equals 0, about any pivot point of our choice. Now let's apply the equilibrium code to real system. A uniform bridge, 24 meters long, and weighing 5 times 10 to the power 5 Newton, is supported by two pillars located 4 meters from each end. So the total length of the bridge is 24 meters. The distance from the first pillar to the end is 4 meters from left. The distance from the second pillar to the end is 4 meters from right. A 2 times 10 to the power 4 Newton car is parked 8 meters from the left end of the bridge. So the distance from the car to the left-hand end is 8 meters. Now, here, since the bridge has weight as well as the car, then the bridge is experiencing two hidden forces. So the force of gravity on the car and the force of gravity on the bridge. Part 1, calculate the force the left side pillar exerts on the bridge. In part B, calculate the force the right side pillar exerts on the bridge. So now, since the bridge is in rotational equilibrium, we can apply the rotational equilibrium condition. But first, we need to choose the position of the pivot. And we're going to choose it in a way that serves our goal in finding FB1. So we're going to choose the pivot at point or at pillar 2. And this is very smart choice because the force at pillar 2 produced zero torque about that point, so it disappeared from the torque equations. Now we draw the tangential direction as well as the radial direction. Remember that the radial direction should pass through the pivot, through the rod, and the tangential direction is perpendicular to the radial direction. So now let's calculate the net torque on the bridge. Remember that we are under rotational equilibrium, so we should expect that the tau net is equal to 0. Now here on the bridge, we have four forces, which means we will need to calculate four torques. And the summation of these torques should be equal to 0. Now let's consider the first force. Let's calculate the torque here. Now we know that the torque is given by plus minus f d cosine theta. Now, the plus and minus here can be indicated by the direction of the rotational effect of this force. The F is the magnitude of the force. The D is the distance between the force and the pivot. And theta here represent the angle between the force and the tangential direction. Now here, since now this force has rotational effect in this way, and which means the direction here will be clockwise. And whenever the force in the clockwise direction, we use the minus sign for its torque. Now the magnitude of the force is missing here. The distance here is defined to be the distance between the point of application of the force and the pivot. And here, the distance should be calculated via the following. We know that the total length of the road or of the bridge is 24 meter. Now, if we removed the 4 meter from both sides, so 24 minus 4 minus 4, and the distance will be 16 meter. Now, for the angle, no need to worry about the cosine because the cosine of the theta is equal to 1, and this is because all the forces here are pointed in the tangential direction. And we know that the angle will be 0, and the cosine of 0 is equal to 1. So we write that the torque of pillar 1 is equal minus the force of pillar 1 times the distance 1. And let's consider the force GC. In order to find the torque, we need first to assign the sign, the magnitude of the force, the distance, and no need to worry from now on the cosine of theta because all the forces are acting in the tangential direction. Now let's start with the sign. The rotation here caused by this force is in the counterclockwise direction, and the force here is positive, so the tau of the GC is equal plus. Now the force of the GC multiplied by the distance between the point of application of the force and the pivot. Knowing that the distance from the car to the edge is 8 meters, the distance from the pivot to the end is 4 meters, the total distance is 24. So we simply calculate the distance from FGC to the pivot by 24 minus 8 minus 4. And the distance will be 12. So the tau should be written as a plus FGC DC. And the DC here is equal to 12. Now, for the FGB, the rotational effect here is in the counterclockwise direction, which means the sign should be positive. So the tau GB is equals to plus multiplied by the force GB multiplied by the distance between the point of application of this force and the pivot. Now here the distance will be calculated in the same way, and this distance will be 8 meter. And why the distance is 8 meter? Because the force here, the FGB, is the force of gravity on the bridge, and it's acting at the center of mass of the bridge, which means at the midpoint. So the distance from here to the end is actually half of the total length, which means 12. Now, the distance from here to here is 12. If we subtract 4 from this distance, then the remaining distance will be 8 meter. And the 8 meter represent the distance between the pivot and the point of application of the FGB. So we write that the FGB is equal plus FGB times the distance B. Now applying the rotational equilibrium, tau net is equal 0. So tau from pillar 1 plus tau of gravity of the car plus tau of the gravity of the bridge is equal to 0, which means minus pillar 1 distance 1. We just substitute the expressions. Remember that we are interested in finding the FB1. We move everything else to the other hand side, which means we're going to move this to the other hand side. It becomes minus. This one becomes minus. Since D1 is multiplied with FB1, then we finally divide over D1. Now we will get that minus FB1 equals minus FGCDC minus FGBDB over B1. Now we multiply both sides by minus, so minus with minus with minus cancelled out. And we will get F pillar 1 equals this relationship. We substitute the values and we will get the final answer for the magnitude of this force, and the magnitude of this force is 2.65 times 10 to the power 5 Newton. Now calculate the force the right side pillar exerts on the bridge. Now here we're going to repeat the same procedure, but this time we're going to change the place of the pivot from FP2 and we're going to move it to FP1. And so pillar 1 will disappear from our equation. So now the pivot will be moved to here. Now we apply the same procedure, and this is going to be the first method, the tau GC and the tau GB with the tau B2. Remember that we are dealing here with the rotational equilibrium, which means the summation of taus equals to 0. We substitute the expression of each of one of these taus. And remember that we are interested in finding the force on pillar 2. So FP2 equals this relationship. We substitute the values, and finally we get the magnitude of the force. Now, the second method, we know that although the object is under rotational equilibrium, but also it's under translational equilibrium, which means the forces acting on the bridge are balanced. So the upward forces are equal to the downward forces, because no need to include the second equation. There is no any left and right forces. So the forces upward are the force from pillar 1, the force from pillar 2, and the downward forces actually are the force of the weights of the bridge and the car. Now we are interested in finding the FP2. Remember that we can get the value of FP1 from the first part. We already did this. FGC is given, which is the weight of the car. FGB is given, which is the weight of the bridge. And the force from pillar 1 has already calculated from part A. And finally, we'll get the same numerical value that we got from first method and first method. Exercise 1. A system of two wheels fixed to each other is free to rotate about frictionless axis through the common center of the wheels and perpendicular to the page. Four forces are exerted tangentially to the rims, and the word tangentially here means they are pointing in the tangential direction, so they are tangent to the circular rim. The magnitude of the net torque on the system about the axis is. So here we are interested in finding the magnitude of the net torque. So we have here four forces acting on the wheel, and we are interested in finding the magnitude of the net torque. And the magnitude of the net torque, the tau net, equals tau 1 plus tau 2 plus tau 3 plus tau 4. Remember, the tau is given by plus minus force times distance times cosine the angle. Plus minus will be indicated from the rotational effect of the force. Now the F is the magnitude of the force, the D is the distance between the point of application of the force and the pivot. And the angle is the angle between the tangential direction and the line of action of this force. However, here no need to worry about the cosine of theta, because the theta itself is equal to 0. All the forces here are pointing in the tangential direction. Now let's start with the first force. Let's call this F1 or tau 1. So tau 1 equals, now this force will rotate the wheel in this direction. This direction is the counterclockwise direction, and the torque will be positive. Now the magnitude of this force is F, and the distance between the point of application of this force and the pivot is this one, which means this is the outer radius, and the outer radius is a 3r. So multiplied by 3r, which means tau 1 is equal 3fr. Now tau 2 is the second force here, and also this force will rotate the object in the counterclockwise direction, which means the torque will be assigned with a positive sign. The magnitude of this force is F, the distance between the point of application of this force and the pivot is associated with the inner radius, and the inner radius is 2r. So we can write that the torque equals 2 plus 2Fr. Now tau 3, let's consider this to be tau 3. Now here this force is rotating the object in this direction, and this direction is the clockwise direction, which means the sign is negative. The magnitude of this force is 2F, and the distance between the point of application of this force and the pivot is associated with the outer radius, and the outer radius is a 3r. So we can write minus 6Fr, and the last force is F. So 4 equals, this force is rotating the wheel in this direction. This is the counterclockwise direction, and the sign is plus in the counterclockwise. The force is F, and the distance between the point of application of this force and the pivot is associated with the outer radius, and the outer radius is a 3r. And we can write that tau 4 is a plus 3Fr. Now we substitute in tau net expression 3Fr plus 2Fr minus 6Fr plus 3Fr. And the final answer is 2Fr, which means the correct answer is C. Now exercise 2, a wheel of radius r is fixed to an axle of radius r over 3 and rotates at constant angular speed omega. Since here we have constant angular speed, then we are under the rotational equilibrium, and the tau net is equal to 0. As shown in the figure above, a force of magnitude F1 is applied tangent to the outer uh, edge of the wheel. So this is pointing directly in the tangential direction. A second force of magnitude F2 is applied tangent to the edge of the axle to keep the wheel rotating at under constant velocity. Also, this one is pointing in the tangential direction. The magnitude F2 is equal to, since the tau net is equal to 0, then the summation of all torques acting on the wheel should be equals to 0. And here, since we have two forces, we will have two torques. In addition to these two forces, we have two additional forces, and they are considered to be hidden forces acting on the wheel. The first force is the force of gravity of the wheel, and it's acting downward, and the reaction from the axle. Now, since these two forces are passing through the pivot, then the torque of the reaction and the torque of this gravity should be equal to 0, and no need to consider them in our calculation. So only two forces are involved in the tau net. The two forces are F1 and F2, which means tau 1 plus tau 2 equals to 0. Now let's find out tau 1. Now the direction of rotation caused by F2 or F1 is in the clockwise direction. In the clockwise direction, we use the minus sign. We assign the minus sign for the torque. Now the magnitude of this force is F1, and the distance between the point of application of this force and the pivot is associated with the outer radius. The outer radius is r. Now for tau 2, this force is rotating the wheel in this direction. This direction is the counterclockwise. For the counterclockwise direction, we use a plus sign. The magnitude of this force is 2, and the point of application between this force and the pivot is associated with the inner radius r over 3. Now, substituting these in our equation, so tau 1 is minus F1r plus tau 2 is F2 r over 3. Now we move F1 to the other hand side. So F2 r over 3 equals F1 times r. R with r cancelled out. We multiply both sides by 3. because we are interested in finding the magnitude of F2. So F2 is equal 3 of F1, and the correct answer is D. Exercise 3 for the wheel and axle system shown above. Which of the following expresses the condition required for the system to be in static equilibrium? And we mean by the static equilibrium, the rotational equilibrium. We know that in the rotational equilibrium, the tau net is equals to 0. Now here we have two visible forces and two hidden forces. The hidden forces are the reaction of the axle and the force of gravity of the wheel. Now, since these forces are passing through the pivot, then the tau of the R and the tau of the force of gravity will be equals to 0. Now, mass 1 will exert force on the inner wheel by its weight. So the weight will acting on the wheel from this side. Let's call it Fg1. And from here we have M2, and the M2 will exert a force by its weight downward on the outer wheel. And let's call this force as Fg2. So Fg1 will produce tau1 and Fg2 will produce tau2. Now let's evaluate tau1 here. The direction of the rotation because of this force is gonna be a counterclockwise direction. So we assign a plus sign for the torque. The Fg is actually the mass times the gravity, and the mass here is m1 times the gravity, multiplied by the distance between the point of application of this force and the pivot, and the distance is associated with the inner radius of the wheel, and it's going to be A. Now for tau2, the direction of rotation because of this force, it will be in the clockwise direction, so we assign the minus sign here. The force of gravity can be calculated by the product of m2 times g, and the distance is associated with the outer radius B. Now we substitute this in our equation. So m1g multiplied by A minus m2g multiplied by B equals to 0. We move this to the other hand side, and the formula becomes m1g times A equals m2g times B. Now g with g cancelled out, so m1a equals m2b. And the correct answer is B. Exercise 4. An experiment is performed by placing a known mass with its center of mass at the distance over 3 meters from the fulcrum, as shown above. An unknown mass is used to balance the system with its distance from the equilibrium not completely measurable. Every time the known mass is changed, the unknown mass is moved until equilibrium is reached. The data that were gathered for this experiment are below. As we can see here, we are changing the mass, but we have kept the same distance from the fulcrum for the known mass. And for the unknown mass, we kept the mass, but we have changed the distance until we obtain the equilibrium. So in the first trial, the equilibrium has been obtained, which means the tau net is equal to 0. In the second trial, also, we have equilibrium, rotational equilibrium, and we can write that the tau net in the second trial is equals to 0. If the mass of the beam is ignored, the value of the unknown mass, so we are interested in finding the value of the unknown mass, and this value, let's call it capital M, which is unknown and fixed in both trials, is most nearly equal to which of the following? Now let's state all the forces acting on the beam. The first force acting on the beam is the weight of the known mass, which is perpendicularly downward. This is Fg1. The second force is the weight of the unknown mass, which is acting also downward. This is Fg2. And there is no force of gravity, or we will ignore the force of gravity because of the beam, because the mass of the beam is ignored. We have only to need to consider the reaction force from the fulcrum. However, the torque, because of this force, equals to 0, since this force is passing through the pivot or the fulcrum. Now, then we can say that after we apply the rotational equilibrium, that the tau1 and tau2 should be equal to 0. Now for tau1, this force is rotating the beam in the counterclockwise direction, and the tau1 should be equal to plus, because it's in the direction of the counterclockwise, And the force here is the mass times the gravity. The mass of the known mass in the first trial is 75 times g times the distance between the fulcrum and the known mass, and this distance is a 3. So tau 1 should be written as 225g. Now for tau 2, this force is rotating the beam in the clockwise direction. So for tau 2, we assign the minus sign. Now, this force has a magnitude of mass times the gravity. However, in the first trial, we don't know what is the mass, and the mass is fixed with unknown value in both trials. And this mass is capital M multiplied by G. This is the force multiplied the distance from the fulcrum. In the first trial, the distance is X. So this becomes minus mgx. So we can write that 225G equals mgx. Now G with G equals, and 225 equals mx. This is the first equation. This equation is a linear equation with two unknowns, where m and x are the unknown. In order to solve this equation, we need to construct another equation. By solving this system of equation simultaneously, we can get the value of m and x. Now, the second equation can be constructed from the second trial. In the second trial, also the equilibrium condition has been obtained. So tau 1 plus tau 2 equals to 0 again. This time, the mass has been changed only. We maintain the same distance from the fulcrum, only the mass has been changed for tau 1. So now the mass is given by 85 kilogram, and 85 kilogram multiplied by G, and for sure it's going to be with the same sign plus because this is counterclockwise, multiplied by the distance from the fulcrum, and the distance is the same. So for tau 1, it should be written as 275 because 85 times the 3 is 275 multiplied by G. Plus the second tau. For the second tau, we maintain the same direction, so it will be clockwise, which means we will assign the minus sign. The m is still unknown, multiplied by G. This is the force times the distance. Now the distance has been updated, and now it's x plus 1. So by moving minus mg x plus 1 to the other hand side, we will be obtain this equation, mg x plus 1. Now G with G cancelled out, and 275 equals mx plus 1. This is the second equation. So we have constructed two linear equations with two unknowns. By solving these two linear equations simultaneously, we can find the value of m and x. Now, how we can solve them simultaneously? We have actually different ways. But for this question, I will use division. So I will divide 2, divide by 1. So 275 divide by 225 equals mx plus 1 divide by mx. Now m and m cancelled out. Now we cross multiply. So 275x equals 225 multiplied by x plus 1. We distribute. So 225x plus 225 equals 275x. Now we move 225 to the other hand side with the x. So we can collect the similar terms in one side. Now 275 minus 225, this is 50x equals 225. And x in this case is 7.5 meter. Now remember, we need to find the mass and not the distance. To find the mass, we use again equation number 1 or even equation number 2, and we substitute the value of x in this equation, which means 225 equals 7.5 multiplied by x. So x is equal 225 divided by 7.5. and this is equal to 30 kilogram. And the correct answer would be C. And that's it for today's lesson on 5.4 rotational equilibrium. Thank you for joining me. See you next time.